What do we
No,
mean by the atomic structure? Any ideas?
no, miss.
First, a hearing of atomic structure.
No, miss.
All right. So when we talk about atomic structure, we're really talking about the structure of an atom. Now, what is an atom? Atom is basically the smallest particle of matter. All matter is composed of atoms. So all matter actually has atoms in it. All right. Any questions so far?
No, miss.
Okay, perfect. So what we're going to be looking at, we're going to be looking on the structure of atoms. We're going to be looking at isotopes in this class, and we're also going to be looking at how we really draw the first 20 elements of the periodic table. How do we represent their structure? Now, it's important to understand the structure of atoms so that we can actually understand the properties of matter. But before we do that, we're going to do a little history of the atom. Now, there were many scientists who put forth different models of what the atoms looked like. So we had different scientists. So in 500 BC, we had Hindu philosophers. Then we had Democritus, we had Lord Kelvin, we have J.J. Thomson, we also had Bohr's atom of the model, and then now we have the modern atom. Now I want each of you to read. Brianna and Jessica are missing, but we're going to start off with Dina Shea. Tell us what the Hindu philosophers discussed.
Hindu philosophers discuss atoms as ultimate pieces of the elements earth, air, fire, and water. Atoms are round and differ in properties such as color, flavor, and odor.
Very good. So that's what they basically did. So that's what the Hindu philosophers did. They basically discussed atoms as ultimate pieces of elements, earth, air, fire, and water, because those were what the scientists studied at that time. Now, after that, we had Democritus. Democritus did something else. Tajina, tell us what Democritus did.
Democritus describes atoms as eternally unchanging and invisible, all made
Indivisible.
of the same substance, and differing only in size, shape, and arrangement in space.
Very good, very good. But then Lord Kelvin came on the scene in 1867. Lord Kelvin basically proposed a vortex model in which atoms are twisted knots or vortices in the ether. So he basically believed that atoms were just some twisted knots going on right there. But then that never lasted very long. In 1904, we had J.J. Thomson coming on the scene, a very popular scientist. Let's hear what J.J. Thomson did, Dina Shay.
J.J. Thomson proposes the plum pudding model of the atom, picturing negatively charged electrons rotating in concentric rings within a sphere of positive electricity.
Very good. So the plum pudding model is attributed to the work of J.J. Thomson. We still look at that today. So the plum pudding model basically had the idea that we have negatively charged particles inside of a round thing that looks like a pudding. So a plum pudding kind of a thing. So the positive charge would be the blue part represented there, and then the brown part would be the negatively charged particles, the positively charged particles. Now, Bohr's atom, Tajina. Tajina?
But Bohr's atom model describes a dense, positively charged nucleus containing nearly all the atom's mass surrounded by electrons traveling in specific allowed orbits.
Very good. So that's Bohr's atom or model of the atom. And then today, guys, we have the modern atom. Now, electrons travel not in orbits, but exist as clouds of electric charge within orbitals that define regions of space with a high probability of containing the electron. So in today's model, we believe that the nucleus is in the center of the atom there, and then surrounding that we have electron shells that contains your electrons. So we believe that the protons and the neutrons are inside of the nucleus, and then outside on the shells we have electrons. So that's what a modern model of the atom looks like. Now, the atomic structure. All atoms are composed of, make notes as you go along, guys. There's a quiz at the end. All right. So atoms are composed. If you want me to stop, just stop me and I'll do that. Atoms are composed of protons. Protons, whenever you think protons, think positive. So your protons are positively charged particles. What kind of charge the protons have, students? What kind of charge?
Positively charged.
Positively charged. The neutrons, no, they are neutral particles. So when you think neutron, just think neutral. You know, like Jimmy Neutron. All right. So the neutrons, they have neutral. They're neutral, meaning it's neither positive or negative. It's zero. Now your electrons very important. Your electrons are negatively charged particles. So this is it. You have your protons, your neutrons, and your electrons. These are what we call your subatomic particles, meaning they're particles inside of the atom. Any questions so far? Everybody's following? Great. Now, protons and neutrons are located inside of the nucleus. The electrons are actually found in orbitals surrounding the nucleus. So the protons and the neutrons, where are they located? Where do we find protons and neutrons?
In orbitals.
Protons and neutrons. One more time. Where do we find them?
Yes, miss.
Nucleus.
In the nucleus. So the protons and the neutrons are located in the nucleus. So this makes the nucleus have a positive charge because the proton is positive and the neutron is zero. So there's a positive and a zero there, which makes it positive. And then outside would be negative because electrons are found in orbitals surrounding the nucleus. We also refer to them as shells, and we're going to see more about that. So this is it now. The positive protons are inside the nucleus, the neutral neutrons, the negative electrons are outside on the orbitals or the shells. So the subatomic particles are really the tiny parts that make up the atom. Very tiny. You cannot see these with your naked eye. So for example, the helium atom, inside of the helium atom, we would have, yes, question?
What can't we see again?
We can't see atoms with our naked eye. They're very small.
Okay.
All right. Helium atom. So the helium atom, this is exactly what it would look like. Inside, you would have the neutrons and the protons inside of the nucleus right here. And then outside, where you see the negative, that would have the electrons outside, floating around on shells.
Neutrons and protons are inside the nucleus?
Yes, so you can write that down. The protons and the neutrons are inside of the nucleus.
Okay, miss.
And then the electrons are found outside on electron shells. Everybody has that?
Yes, miss.
Yes, miss.
Where is Brianna and Jessica? All right, so this is the proton, this is the neutron, this is the electron, this is the shell. Now, this is just to summarize what we've done so far. The proton has a charge of +1, positive. Neutron is neutral, meaning it's 0. Electron is -1. And just to give you an addition in terms of the mass of the proton is 1. Mass of the neutron is also 1, but the mass of the electron is 1 over 1,836. These are the symbols that we use to represent them. We have protons, P, neutrons, N, electrons, E. So you can screenshot this or take a note, take it off. So let's write it off. So by now you should have finished writing this off and ready to go again. Ensure that you have these because we have a quiz coming up at the end, all right?
Yes, miss.
Perfect. Now, every different atom has a characteristic number of protons in the nucleus. So that's what makes that atom unique, because they'll have specific number of protons, specific number of neutrons, and specific number of electrons. And I'm going to be showing you in this class, how do we really identify how many protons, how do we identify how many neutrons, and how do we identify how many electrons a particular atom has. But by now, you should know the names of the first 20 elements of the periodic table. Do you know them? Can you say them?
No, miss.
Can you say them, Tajina? Can you say them, Tajina?
This is a lot to just memorize and say it like that.
It's not hard. Remember, we did a challenge where we memorized them in a previous class. I think you probably missed that class, but we did. Tajina, unmute because I know you know how to do it. Come, Tajina.
It's a lot.
It's not that hard. 20, we're going to learn it today. Tajina?
Miss, you remember back then when you...
20 elements of the periodic table are, you ready for them? So the 20 elements are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. I expect you to know them by the end of this class.
Miss, you're the teacher. You can remember them.
No, and you're the student. Very important that the student knows them. Even more important than the teacher. All right? Very important, right, Dina Shea? Because guess what? The student has a chemistry exam next week.
Oh, great.
Yes, that the teacher will be marking. And I need the student to do well. All right? So we're going to be studying them.
In order for us to do well, you don't make it hard, you know?
No, not going to be hard. It's going to be everything that we'll learn. All right? So every different atom has a characteristic number of protons in the nucleus, all right? Now, the atomic number, very important. The atomic number is equal to the number of protons. Very important that you write that down. The atomic number is equal to the number of protons. Atoms with the same atomic number have the same chemical properties and belong to the same element. And how do we know the atomic number? The atomic number is like you're counting. So for hydrogen, it's gonna be 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, sodium 11, magnesium 12, aluminum 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18, potassium 19, calcium 20. That's the atomic number for the first 20 elements of the periodic table. There is a slide that I have here which shows you the first 20 elements. You can probably write that off when I reach there, but write this off or screenshot it, all right? Tell me when you have it. Have it already? Have it now?
Miss.
All right, perfect.
Yes, miss.
Perfect. Now the atomic structure. Each proton and neutron has a mass of approximately 1 Dalton. So the mass is like 1 Dalton, named after Dalton, who did some work in the atomic structure. The sum of protons and neutrons is the atom's atomic mass. So you can write this pointer off. The sum of protons and neutrons is the atom's atomic mass. And then we're going to look at isotopes. So write that down. When we talk about isotopes, we're talking about atoms of the same element that have different atomic mass number due to different number of neutrons. I'm going to send you this video so you'll have it to look back on. So the atomic structure is usually written like this. Some books will have the 4 at the top, some will have the 2 at the top. So helium is a symbol, He. The 4 is the mass number. So the bigger number is always the mass number. Whether it's at the top or at the bottom, the bigger number is the mass number and the smaller number is the atomic number. So see there, the atomic number, which is the number of protons in the atom, and then the atomic mass, which is the number of protons and neutrons in an atom. Number of electrons is equal to the number of protons. An atom will have the same number of protons as electrons because an atom is neutral. So the atom must have same positive as well as negative. So write that off, that the number of electrons is equal to the number of protons. Atomic number. We usually use Z to represent that. That's the number of protons in the nucleus. Mass number. So we're summarizing what we've said so far. Mass number is equal to the number of protons plus the number of neutrons, which is the atomic number plus the number of neutrons. Isotopes, sorry about the E missing. They are atoms of the same element X with different number of neutrons in the nucleus. So here we have it written out here. So this is the element symbol, this is the mass number A, and Z is the atomic number. So let's do that again. Element symbol is X. A is the mass number and Z is the atomic number. Okay, students? Now, this is how it would look. So for hydrogen, there are 3 isotopes of hydrogen, but I'm going to go into isotopes soon. So this is how it would look. So the mass number is at the top and the atomic number is at the bottom. So some isotopes are hydrogen. Isotopes are really atoms of the same element with different number of neutrons in the nucleus. In other words, isotopes, they will have the same atomic number, but different mass number. So the bottom number would be the same, but the top number would be different. So you realize that hydrogen, it's 1 constantly because that's what makes it hydrogen. But the mass number changes because there are different number of neutrons inside of the hydrogen. So we have 3 isotopes of hydrogen. We also have 2 isotopes of uranium. So the uranium, the atomic number is 92. So the 92 there represents the atomic number, but the 235 and the 238 are the mass number because the number of neutrons is different. Can you guys calculate the number of neutrons in the first hydrogen? How would we find the number of neutrons in the first hydrogen? Let's try that. All right, so we just calculated the atomic we just calculated the subatomic particles for hydrogen and for helium. Could you just remind me what you have for helium again? What's the mass number for helium? What's the mass number, Tajina?
Miss the mass number.
You have it correct. Continue. Mass number is? The 4, remember?
Yes, miss.
All right, so the mass number is 4. What's the atomic number?
The atomic.
What's the atomic number?
2.
2, very good. And what's the number of electrons? How many electrons does it have for helium?
2, miss.
How many?
2.
Very good, very good. And how many neutrons?
2, miss.
Very good. Excellent. So now we're getting it. Good job. All right. Good job so far. All right. I love it. So here is it now. These are the first 20 elements of the periodic table. You have to know them like how you know your name. So when I
Yes,
ask you
miss.
them, you must be just spelling them. So let's run through them. So you will just call all 20 for me.
Yes, miss. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon,
Mhm.
sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium.
Good job. Good job. So these are the first 20 elements of the periodic table. This now shows you the mass number and the atomic number for the first 20 elements of the periodic table. So take a picture of these or write them off. Which one you're going to do? You're going to take a picture or you're going to write them off?
Take a picture, miss.
All right. So take a picture. You must know them, please. Thank you. So take a picture real quick.
Yes, miss. Got it.
Great. So this is going to help you. Let me know when you're finished.
Got it, miss.
Perfect. So this is how the atomic structure really is all about. We just did some examples of that in terms of the protons, the neutrons, and the electrons. At the end of this video, we're going to draw it for all 20. So you did the first two, so we're going to do the remaining 80. But this 18, sorry, this is our carbon 12, carbon 13, carbon 14. So when we're drawing atoms now, Tajina, there is a rule of assigning the electrons on the shells. Remember that we said that there were shells that these electrons are on. So the first shell can hold 2 electrons. So the first shell holds a maximum of 2 electrons. So make a note of that. This is what it's pointing to. The first shell holds 2 electrons. The second shell holds a maximum of 8 electrons. The third
Okay.
shell, it actually holds a
32.
maximum of 18 electrons. But
Oh,
in this level, we actually do the first 8 first, and then we go on to the fourth shell, which can hold a maximum of 32. So
miss, I always get excited when I'm doing the shells,
you love the
miss.
shells? Great.
Yes,
I'm already
miss.
excited. So we're going to be having, that's what we're going to be doing at the end. We're going to be doing the shells. Nice, nice, nice. Now, example, draw the potassium atom. Number of protons. How many protons would potassium have? How many protons?
19, miss.
Very good. 19. What about electrons? How many electrons would potassium have?
19.
Excellent. And how many neutrons would potassium have?
20, miss.
Excellent. So we write down the number of protons first, then we write down how many neutrons and how many electrons, and then we start putting them on shell, which is the exciting part. So how many can we put on the first shell?
2, miss.
2. Very good. So the first level, 2 maximum. What about the second level?
8, miss.
8. Very good. And what about the third level?
18.
Well, it can hold up to 18, but we're going to put 8 first as the maximum. So we're going to assume that it can only hold 8 at this level, all right? Because there is something else, but you learn it as you go on to study deeper in chemistry. So at this level, we put in 8 as the maximum. So we'd put
Yes,
only
miss.
8 on the third shell. That's the maximum for now. And then we would put the remainder on the last shell. How many would we have remaining?
For the okay.
Last shell.
You have 2 on the first one. Hold on, miss.
No problem. So 2 on the first one. So we have only 1 remaining for the last shell. So it's 2 on the first shell. And that now gives rise to our electronic configuration, EC. So you would write EC is equal to 2 on the first shell, comma, 8, that's the second shell, comma, 8 for the third shell, comma, and 1 for the last shell. So the electronic configuration of potassium would be 2, 8, 8, and 1. See how we got that?
Yes, miss.
All right. Now, what are isotopes? You're going to read for me.
Isotopes are variation of chemical elements that have the same number of protons but different numbers of neutrons.
Excellent. So it's just a variation of the chemical element. It will have the same number of proton, which is the same atomic number, but the number of neutrons and the mass number will vary. All right. So examples of isotopes, we have hydrogen 1, hydrogen 2, hydrogen 3, helium 3, helium 4, carbon 12, carbon 13, carbon 14, nitrogen 14, nitrogen 15, oxygen 16, oxygen 17, oxygen 18, uranium 235, and uranium 238. So these are all examples of isotopes that are very popular. Sodium also has isotopes. So this is how sodium isotopes look, or the structure of sodium isotopes. Now, radioisotopes can be used in the scientific field, in application research. It can be used in various different facets of our scientific life. No, carbon 14. We usually use carbon 14 for carbon dating of organisms and substances. So like your archaeology, when you want to find out how old a substance is, you find something and you want to find out how old it is, or research to determine steps involved in plant photosynthesis. We use phosphorus 32 and 33 in research involving biology and genetics. We use selenium 75 for protein studies in life science. We use strontium 85 for metabolism and bone formation studies. And we use hydrogen 3 or tritium to study life science and drug metabolism. All right?
Yes, miss.
Cobalt 60 for radiation therapy to prevent cancer. Iodine 131 to locate brain tumors or liver and thyroid activity when you want to monitor cardiac, liver, and thyroid activity. Carbon 14, we also use it to study metabolism changes for patients with diabetes, gout, and anemia. Carbon 11, we use it to tagged onto glucose to monitor an organism during a PET scan or PET scan. Sodium 24 for blood circulation to study that. Thallium 201 to determine the damage in heart tissue, detection of tumors. And we also use technetium 99M to locate brain tumors and damage heart cells. Radio tracer in medical diagnostics, that's the imaging of organs and blood flow studies. All right, so you can do this list. Americium 241, what do we use it for?
Test integrity of boilers and aircraft parts.
That's for iridium 192, the top one, americium 241.
Americium.
For
For
uniform
uniform
thickness.
thickness, when rolling steel and paper, determine the location of oil wells.
Good, good. What about sodium 24?
Oil well studies and to locate leaks in pipelines.
Iridium 192.
Test integrity of boilers and aircraft parts.
Uranium 235.
Nuclear power plants and naval
Propulsion systems.
propulsion system fuel production of fluorescent glassware and colored wall tiles.
Good. And californium 252.
Determine moisture content of soil, important for road construction and building industries.
Awesome. Thank you. So what you're realizing is that isotopes are very important to us in everyday life. We use them. All right.
Yes, miss.
History of the atom again. Niels Bohr, he did some work on that. What he did, he really studied under Rutherford at the Victoria University of Manchester. He refined Rutherford's idea by adding that the electrons were actually in orbits rather like planets orbiting the sun. So with each orbit only able to contain a set number of electrons. And that's what we were doing earlier before we did isotopes. So I want you to jot down some uses of isotopes in addition to the ones that we just did.
Yes,
All
miss.
right. Now we have some activities. So for our activities, after the persons who are going to watch this recording, like and share and subscribe, Tajina and I are going to do some activities now that we're also asking you to complete. So like the people who missed class and the people who are just watching this video right now, these are the activities. All right, Tajina? So
Yes, miss.
we're going to be selecting an element from the first 20 elements of the periodic table. So any element, you can select one from hydrogen right to calcium. We're going to create a 3D model of the element to show the number of protons, neutrons, and electrons. Then we're going to do a brief research on the selected element. Then we're going to draw the atomic structure of the first 20 elements of the periodic table and submit to your teacher. All right?
Yes,
This
miss.
is the final activity. Thank you so much for watching and viewing. We're actually finished.
Yes.